So last class we started our discussion of reasoning and how we come to conclusions by talking about inductive reasoning. And we sort of discovered that people are kind of bad, right, at reasoning to make good conclusions, to come to good decisions. So there's bias that can creep in, and we're bad at falsifying our beliefs. Once we have a belief, we tend to stick to it. So today we'll review deductive reasoning, which is a little bit different than inductive reasoning. Deductive reasoning is based on the rules of logic, and I'll explain the difference in the next slide. So last class we talked about inductive reasoning, and the idea there is that you're taking some evidence to draw a conclusion that's necessarily probabilistic. So it can never be 100% certain. Deductive reasoning is a bit different because we can actually come to certain conclusions that must be correct if they follow logically from the evidence. And so the way deductive reasoning works is that we start with some sort of broad principle, and based on that broad principle or principles, we make logical predictions about specific cases. So we're starting broad, and we're ending at a very specific prediction. Now you can contrast that with induction, where we're starting from a few cases, a few observations, and ending at some broader prediction. So a little bit different. An example of deductive reasoning, take these three statements. All people are human, right? Necessarily true. Sherlock Holmes is a person, therefore Sherlock Holmes is human. That conclusion logically follows from the two statements that came before it, and because of that it's necessarily true. Now, the form that is used in deductive reasoning is known as the syllogism. And this was introduced by Aristotle, so back in ancient Greece. And the idea here is that in the syllogism we have two broad statements, or premises, that lead to a conclusion. So in this example, premise 1, all men are mortal. Premise 2, Socrates is a man. Conclusion, Socrates is mortal. And that conclusion is correct because the two premises that it's based on are also correct. And they follow logically. The conclusion follows logically from premise 1 and premise 2. So a syllogism is always valid when its conclusion follows logically from the two premises that come before it. Now, just because a syllogism is valid, just because it's logically valid, doesn't mean that it's true. Right? So if one of the premises is false or not true, we could still have a valid conclusion that is a false statement. So here's an example. Premise 1, all birds are animals. That's correct. Premise 2, all animals have 4 legs. That's incorrect. And so this leads to the valid but incorrect conclusion. And when I say valid, I mean logically valid. A logically valid conclusion based on the statements that came before, all birds have 4 legs. So that's a false statement, but the conclusion is valid based on the rules of logic. So there's an important distinction there. Valid doesn't necessarily mean true. It means that the conclusion follows from the statements that came before it. So I've just thrown a lot of logic at you, and you might be thinking, am I in some sort of philosophy class? Cognitive scientists are interested in whether we think logically. So when we make decisions, when we reason, do we use the rules of logic? And the fact that invalid syllogisms, so syllogisms that have a conclusion that doesn't follow from the statements that came before it, can have believable conclusions, has been sort of exploited by cognitive psychologists to examine whether we think logically. So here's an example of a syllogism that is invalid, but has a believable conclusion. Premise 1, all students are tired. Premise 2, some tired people are irritable. Conclusion, some students are irritable. So that second premise leaves open the possibility, right, that people who are irritable are not students. And that's why the conclusion is invalid. But it's a believable conclusion. And so Evans et al. In 1983 had participants read valid and invalid syllogisms, like the one you just saw, with both believable and unbelievable conclusions, and state whether the conclusion logically followed. So here's an example. No cigarettes are inexpensive. Some addictive things are inexpensive. Some addictive things are not cigarettes. So that's a valid conclusion. It can be, it's valid based on the rules of logic. So it follows from the statements that came before it. And these can be quite tricky. So I'll go through them kind of slowly. Here's an example of one with an invalid conclusion. No addictive things are inexpensive. Some cigarettes are inexpensive. Some addictive things are not cigarettes. The valid conclusion would be some cigarettes are not addictive. But that's unbelievable. So we have this invalid conclusion that is believable. Some addictive things are not cigarettes. And what they found was that whether or not the final statement actually logically followed from the statements that came before it didn't really matter. All that mattered was whether the conclusion was believable or not. And so we can see that in this bar plot here. If the conclusion is logically invalid but it's believable, people accept it. So we're pretty bad at evaluating, right, whether a conclusion sort of logically follows from the evidence that comes before it. And you probably saw that, right, in the last slide. It was kind of difficult to figure out exactly why that conclusion was valid or invalid. And so this is known as belief bias. We tend to think that a syllogism is valid if its conclusions are believable. So to put that another way, if a conclusion is believable, we ignore whether it was logically derived. So we're seeing some evidence here that when we are making decisions, when we're reasoning, we're not necessarily always using logical thinking. So cognitive scientists have also looked at our ability to assess what's known as the conditional syllogism. And a conditional syllogism is a special form of the syllogism that can be cast as if P then Q. So I should say it's a syllogism that has the form if P then Q. And what's nice about syllogisms in this form is that there's basically a mathematical formula that tells us whether the conclusion is valid or not. So if the statement has this form, if P then Q, and P is true, then Q must be true. We call this modus ponens, which is Latin, and it means the way that affirms by affirming. If the statement is of the form if P then Q, and Q is false, then P must be false. We call this modus tollens, which means the way that denies by denying. So let's work through the example of modus ponens here on the screen. If I study, I'll get good grades. So we have this if P then Q form. P is true, I studied. Therefore, we can conclude with 100% certainty that you'll get a good grade. So because P is true, Q must be true. So that's modus ponens, the first valid form of the conditional syllogism. The second is modus tollens. So if I study, I'll get a good grade. Now, if Q is false, we can conclude with certainty that P is false. So you didn't study, you didn't get a good grade, therefore you didn't study. So this is the second form of the valid conditional syllogism. Now there are also invalid forms. The first is known as affirmation of the consequent. So if Q is true, this doesn't really tell us anything. We can't come to some logical conclusion. So if I study, I'll get a good grade. You got a good grade. Does that mean that you studied? Not necessarily. You may have studied, you may not have studied. Another invalid form of the conditional syllogism is known as denial of the antecedent. If I study, I'll get a good grade. So if P is false, again, we can't really conclude anything. We can't come to some logical conclusion. So if I study, I'll get a good grade. You didn't study. It's unclear what's going to happen now, right? You may get a good grade, you may not get a good grade. There's no conclusion that we can draw when P is false. And so what's nice about conditional syllogisms is that there are this very clear set of rules that they're governed by. So if the statement is set up as this, in this if P then Q format and P is true, Q must be true. If the statement is set up such that, if P then Q and Q is false, P must be false. On the other hand, we know that if we have a conditional syllogism and P is true, that doesn't tell us anything. If Q is false, that doesn't tell us anything. So let's do another example. If it is a dog, then it smells. If P, then Q. So what can we conclude here? If P is true, right, then it must smell. So if it's a dog, it must smell. If Q is false, then we can conclude that P is false. So if it doesn't smell, then we can conclude with certainty that it's not a dog based on the rules of logic. And again, we have the two situations where we can't reach any conclusion, right? So if Q is true, if it smells, could be a dog, could be something else. If P is false, if it's not a dog, it could smell, it could not smell. And so we can use these rules to investigate whether humans solve problems logically. And so this was first tackled using what's called the Wasson four-card problem. And we talked a bit about Peter Wasson in the last lecture. He was interested in whether we use induction, how we use induction to solve problems, and he found, right, that we fall prone to confirmation bias. We often fail to attempt to disprove our beliefs. We only look for evidence in support of our beliefs. And so here he's looking at deduction, and he's using the conditional syllogism as his sort of model system. And so in the Wasson four-card problem, you're given 4 cards and you're told some rule that governs what's on each side of each card. And your task is to flip over the cards that falsify the rule. So if there's a vowel on one side, then there's an even number on the other side. That's the rule. And so we have our 4 cards, A, K, 4, 7. And now your task is to flip over cards that falsify the rule. And what's nice here is that because this is set up as an if P then Q statement, we know that there are only 2 possible cases that can lead to some logical conclusion. Put another way, there are, 2 cases here that we can use to falsify this rule. Right? So if P is true, then Q must be true. So if we flip over the A, a vowel, then we must find an even number on the other side. If we don't, we falsify the rule. The other thing we know is that if Q is not true, then P is not true. So if we flip over the 7, right, and we find a vowel, then we've also falsified the rule. Because the rule is if there's a vowel on one side, then there's an even number on the other side. So in the case of not Q, for the rule to stand, there must be a consonant on the other side. The other two cards don't really tell us much. 4 is quite tempting to flip over, but 4 only allows us to affirm the rule. It doesn't allow us to falsify the rule. So in this case, the key here is falsification. And we talked a little bit about this last lecture. Wasson was also interested in falsification, right? And he found that humans are very poor when it comes to looking for evidence to falsify their beliefs. And we see the same thing here. We're very poor at using the rules of logic, in this case, to falsify a rule. So again, the only way to falsify this rule is by flipping over the A or the 7. Finding an odd number on the other side of the A falsifies the rule. Finding a vowel on the other side of the 7 falsifies the rule. What do people do? So participants are good at identifying that the A needs to be flipped over, but they often also say that the 4 needs to be flipped over, even though there's no possible way that flipping over that 4 can falsify the rule, right? If you flip it over, you can affirm the rule. If you flip it over and you find that there's a vowel, great. If you flip it over and find that there's a consonant, that's meaningless, right? Because the rule is that if there's a vowel on one side, there's an even number on the other side. So participants are pretty bad, it seems, at using the rules of logic to solve problems like this. And this has been shown over and over and over again. This paper that's cited here is actually a meta-analysis. So it's a paper examining the results of many papers that have used this Wasson 4-card problem. And consistently what's found is that people will go with P and Q, even though Q doesn't solve the problem. So you want to pick P and not Q if you are following the rules of logic. So we can ask, does performance improve if the rule is less abstract? So maybe if we sort of make this problem more based in the real world, people are better at thinking logically, better at falsifying rules. So here's an example of that. This is from a study run in the 80s, where they attempted to take the conditional syllogism and make it, a bit more sort of like what you would encounter in the real world, a problem that you would encounter in the real world. So here's the rule. If a person is drinking beer, then they must be over 18 years of age. And you have to falsify the rule by flipping over 2 cards. So obviously flipping over beer, right? If you find that on the other side of that, the age is under 18, you falsify the rule. Flipping over 16, not Q, could potentially also falsify the rule, right? So not Q means that P must also be false. So if we flip over 16 and we find beer, we falsify the rule. And what we actually find here is that people are a little bit better at this task because it's sort of more grounded in the real world. So 73% of participants actually got this. They picked the card with beer on it, or they picked the card with 16 on it. And they weren't as tempted by the card with 22 on it, which, can affirm the rule, but it can't falsify the rule. And so there's some evidence that we're actually better at thinking logically in tasks that are sort of more grounded in the real world. And some other studies have used the Wasson 4-card problem with tasks that are sort of more grounded in the real world. We would say that they have more ecological validity. So why is that? Well, one idea is that real-world tasks, like the one we just saw, activate what's called a permission schema. Schema is a mental model. In this case, it's a mental model of how things should work. And so the idea is that this permission schema actually focuses our attention more on falsification. And so we're a little bit better at identifying the situations, or the cards in this case, that falsify the rule. And we're less likely to be tempted by the cards that simply affirm the rule. So we've come to the end of the lecture and the lecture review. Question 1, what is deductive reasoning? Question 1, what is deductive reasoning? Deductive reasoning starts with broad conclusions to generate predictions based on the rules of logic. Question 2, what's a syllogism? Question 2, what's a syllogism? A syllogism consists of two broad statements called premises that lead to a conclusion. Now, the key here is that if the premises are true and you follow the rules of logic, then the conclusion is necessarily true. Question 3, what does the Wasson task suggest about whether humans think logically? Question 3, what does the Wasson task suggest about whether humans think logically? The Wasson task suggests that we struggle to follow the rules of logic, especially for problems that are more abstract.